Problem number 3, we're given this figure up above. It says 3 charged particles are placed as shown on the graph exactly at the intersection of whole number grid lines. So that's kind of nice. Part A says calculate the combined field due to these charges at the indicated point 2 meter, 1 meter. So all these values that are on the x and y axis are in meters. So let's just write some stuff down. So I know that Q1 has a charge of 1 microcoulomb. It's positive 1 microcoulomb, so 1 times 10 to the negative 6 coulomb. And that's located at negative 1, 1. We know Q2 is a negative 4 microcoulomb, and that's located at negative 1, negative 1. And then we know that Q3 is 3 microcoulomb, so 3 times 10 to the negative 6 coulomb, and that's located at 2, negative 1. So that's where we're located. And we're interested in finding the electric field at 2, 1. That's what we're interested in. So we're interested in electric field at that spot. And here's the thing. There's nothing actually there. All these charges are interacting with each other, but we're not interested in that. We're interested in how are they all communicating to that location. There's nothing there. Now, is Q1 forcing Q2? Sure, they're forcing each other together because they're opposites. Is Q2 forcing Q3? Sure, they're attractive because they're opposites. Is Q1 forcing Q3? Sure, because they're opposite. Excuse me, they're the same charge, so they'll be pushing each other apart. But we're not interested in the forces between them. Remember that equation would be F equals K, whatever 2 charges I'm interested in over the distance between them squared. It could be Q1, Q2, Q2, Q3, Q3, Q1, doesn't matter. All right, that's force. There's nothing there, so it's no force. So do not use that equation here. So if I want to find the electric field around charges, the electric field I want to find is E equals K, the Q producing that charge over R squared. It's absolute value. So E1 would be K Q1 over R1 squared. Now, how would I determine R1? Well, R1 would simply be the distance from here to that point. In this particular case, it's pretty easy to figure that out because take a look, 1 meter, 2 meter, 3 meters. So R1 is 3 meters. Okay, so I want to do that. Let's go ahead and do that first. So this is 9 times 10 to the 9th newtons times meter squared over coulomb squared. Q1 is 1 microcoulomb, so 1 times 10 to the negative 6 coulomb, absolute value, all over 3 meters squared. So if I do that, give me a second to punch in my calculator. So 9 e to the 9th times 1 times 10 to the negative 6, excuse me, e to the negative 6 divided by 3 squared. So I didn't write that, but that whole thing is squared, not just the meter squared. And I get a value of 1,000. So this is 1,000 newtons per coulomb. The unit meter squared will cancel with meter squared, and one of these will cancel with there, so I get newtons per coulomb. If I look at the direction that's positive, remember positives radiate out, so that would be to the right. So I just put a little arrow to the right to help me out. So Q1, if it was the only charge there, would be acting with an electric field of 1,000 newtons per coulomb 3 meters from itself. And in this particular case, since the point of interest is to the right of it, it would be pointing right. Okay? So let's look at now Q3. Or just give me Q2. Let's go in order. So now E2 is K Q2 over R2 squared. All right. What is R2? This one's going to be a little bit more tricky. See, R2 is from here to there, right? Well, if I notice, take a look, I'll do this in red so you can see it. There's a base right here and there's a height right there. So R2 would technically be 3 meters squared plus 2 meters squared, 3 here and 2 there. And then I would square root that. And so if I do that, 3 squared plus 2 squared, I get 13. I then take the square root of that, and I get 3.6. So the R2 is 3.6 meters away. So that's this value. That's 3.6 meters there. So now I can plug in, and I get that 9 times 10 to the 9th newtons times meter squared over coulomb squared. Q2 is a negative 4, but because absolute value doesn't matter, times 10 to the negative 6 coulombs all over 3.6 meters squared. If I punch all that in, I get 9, 10 to the 9th times 4 times 10 to the negative 6 divided by our 3.6 squared. And so I get 2769. So I'm just going to call that 2770 newtons per coulomb. And that's kind of at an angle. We don't like that because we got to break it up into components. See, this one we don't have to worry about because it points in the x direction. This one we do. So now here's the thing. I actually drew that wrong. it should be like this. Why is it down? Oh, because it's negative, and negatives pull in. Okay? And then Q3, I'll just do that really quickly up here. Q3, what is its R value? That's pretty easy. It's just 2. And so E3 equals K Q3 over R3 squared. Let's plug that in. That's 9 times 10 to the 9th newtons times meter squared over coulomb squared. I'm going just a little bit more quickly here. Q is 3 times 10 to the negative 6 coulombs all over 2 meters, that whole thing squared. All right, and so if I do that, 9 times 10 to the 9th times 3 times 10 to the negative 6 divided by 2 squared, I get a value of 6,750 newtons per coulomb, and that's directed straight up because it's positive. Okay? So what I'm going to do is I'm going to look at just that spot right there, and I'm going to draw a little diagram. So here's my little spot right there. We are feeling a 1,000 newtons per coulomb to the right. He's feeling a 6,750 newtons per coulomb straight up, right, because of that guy right there. And then at some angle, he's feeling 2,770 newtons per coulomb kind of at an angle. So I didn't draw that to scale, but you guys can see that idea. So what I need to do is I need to find that angle right there, because that angle and this angle correspond to the same thing. So see this little angle right there? That's the angle that's pulling down below this negative x-axis. So how do I determine that angle? Well, I can find any angle if I know a right triangle. If I look really quickly, make this a little bit bigger, so you can see this. You see this right here? That right there is my triangle. All right? And so if I know the adjacent to that angle as well as the opposite to that angle, which I do, the adjacent is 1, 2, 3 meters over the and then the opposite is 2 meters, I can use the inverse tan function. So theta is the inverse tan of the opposite side, which is 2 meters, over the adjacent side, which is 3 meters. They'll cancel. And so if I do the inverse tan of 2/3, I get 33.7. So this is 33.7 degrees is that angle. So I'm going to come down here, and this is 33.7 degrees. So what I'm going to need to do is I'm going to need to take this E2, that's E2, E3, and E1. I'm going to have to break up E2 into E2x and E2y. Now E2x would be that value right there, and then E2y would be this. So this E2 in the y direction, E2 in the x direction. E2x would be 2,770 newtons per coulomb, cosine of 33.7 degrees because it's adjacent. And so that's 2,770 times cosine of 33.7, and I get 2304.5 newtons per coulomb, and that is to the left. And then E2 in the y direction would be 2,770 newtons per coulomb sine of 33.7 degrees because it's opposite. That's the opposite side. So 2,770 sine of 33.7. And I get 1536, but I'll write that to 1537 because it's 1536.9. So 1537 newtons per coulomb, and that is down. So how many electric fields do I have? Take a look real quick. I'm going to redraw this picture. I have that one, which is 1,000. That's E1 newtons per coulomb. I have that one, which is 6750 newtons per coulomb. That is E3. I have that one, which is 2304.5. That's E2 in the x direction, and then I have that one, which is 1537. That's E2 in the y direction, is newtons per coulomb. All right, so what can I do with that value and that value? I can subtract them. So E in the y direction would be all of them added up in the y direction. So you don't need to show a formula. It would be just 6750 newtons per coulomb minus, let me make that a little smaller, 1537 newtons per coulomb because they're going in the opposite direction. Or if I choose up to be positive and to the right to be positive, that would be the positive value. That's the negative value. So 6750 minus 1537, I get 5,213 newtons per coulomb, and that is up because it's positive. And then EX would be all the X ones. There's 1,000, so that's positive because it's going right, minus the one, or plus an opposite, 2304.5 newtons per coulomb. And so I get a negative 1304.5 newtons per coulomb. The negative sign simply means it's going left. Or I don't have to have the negative sign. I can just say left. So that is X. That's the X part. And this is the Y part. So what I can do now is I can think of that spot having that much in the y, and that much in the x. Well, how do I add them? Well, if I start in that spot, remember this is 2, 1, that spot, I have 1304.5 newtons per coulomb going left, and then I have 5,213 newtons per coulomb going up. That is my resultant. So how do I get that value? That's the resultant electric field. And then I would also need to know that angle. So how do I get the resultant? I take the total square foot. So the total E is equal to 5,213 newtons per coulomb squared plus 1304.5 newtons per coulomb squared, square rooted. That would give me my magnitude. And then the direction is the inverse tan of opposite. So the opposite would be 5,213 newtons per coulomb all over 1304.5 newtons per coulomb. Those would cancel. And so let me do the Pythagorean theorem first. I get 5,213 squared plus 1304.5 squared. I then will square root that, and I get that the electric field in magnitude is 5,374 newtons per coulomb. That's the magnitude, and then it points at a direction of whatever the inverse tan of 5,213 divided by 1304.5 is, and that's 76 degrees, so 76 degrees. And that, remember, that's north of the west, so that's north of west by how I have it pictured, because it's in the second quadrant. And so E as the vector is 5,374 newtons per coulomb at 76 degrees north of west. That's the electric field. Okay, so part B says now you take a 1 nanocoulomb charge is brought to that spot. What is the magnitude and the direction of the force on this charge? Hint, you already know the electric field at that location. And so I've already written down the electric field at that location. And we got that from doing this part right here, right? The 5374 at 76 degrees. So what we're doing now is we know the electric field at that spot. Let me zoom in a little bit. We know the electric field at that spot. You are now bringing in a charge to that spot, okay? He feels the electric field that is already there, all right? What is that electric field? We have that on the next page. And so the electric field is that value right there. All right, it's a 1 nanocoulomb charge, excuse me. It's a 1 nanocoulomb charge. And so what I can do is I know that F is equal to QE. I already know the electric field. There's no reason for me to find the forces, because what would be miserable is to go back and find the force between those two, find the force between those two, the force between those two, and the force between those two, and now have to add all those up again just like we did. But since we've already done all the legwork with the electric field, we're good. And so I already know the electric field, so Q jumps around on me right now. Q is equal to 1 nanocoulomb, so 1 times 10 to the negative 9th coulomb, times my electric field, which is 5,374 newtons per coulomb. If I do that value, so 5,374 times 1 times 10 to the negative 9th, I feel a force of 5.374 times 10 to the negative 6th newtons, because coulomb and coulomb cancels, and that's my force. But because it's a force, remember forces are vectors, there's also a direction. Because the charge is positive, he'll go in the direction of the electric field, so he would be going at 76 degrees north of west. He would get pulled that way. If for some reason this was negative, what does negative mean? Negative means opposite. So it would still be 5.374 times 10 to the negative 6 newtons at 76 degrees. But instead of going north, he would want to go south. And instead of going west, he would want to go, you said it, east. So it would get pushed 180 degrees different because it would be negative. So the force on it, because it's still 1 nanocoulomb would still be the exact same value, but the direction would be 180 degrees difference. So because it's force, it says what's the force on the charge? That implies both magnitude as well as direction.